Okay, we're seeing a surge in transaction volumes, and in particular in number of transaction outputs, which have led several wallet applications, in particular the popular ones such as YWallet Lite and Nighthawk, to stop working. So people have started to try to migrate their wallets to YWallet because it has a better scalability than YWallet Lite and Nighthawk. So today in this test, we are going to push YWallet to the limits, or at least try to see how it behaves under a heavy load by creating an account or creating 100 accounts. So to do so, what I'm going to do is take a YWallet, create one account, and then from that account, I'm going to create 100 sub-accounts. So for that, I can go to, I select the account, I go to the new sub-account option, and I'm I entered 99 as the number of sub-accounts. So now I have 99 sub-accounts and one main account for a total of 100. And I can see that the last sub-account has an index of 99. So there are really 100 accounts here. So we're talking about 100 different secret keys. All these accounts are unrelated. They have the same seed phrase, but as far as the system, the blockchain is concerned, all these 100 accounts have different viewing keys and therefore have to be trial decrypted separately. So it's just a shortcut for actually creating 100 accounts, and which is pretty much the same way as what would happen to you if you are using a YWallet Lite and you were pushing the button new shielded address 99 times. You would also have 100 addresses, 100 shielded addresses, and these addresses would actually match the ones that YWallet creates. So that's pretty much what would happen to you if you had an account in a wallet in YWallet Lite, and you had 100 shielded address there, and you had to migrate that wallet to YWallet. So in YWallet, you would have 100 different accounts. All right, so what that being done, now what we can do is do the actual rescan. So for that, I'm going to go to the settings, and I'm going to make sure that I have set the server to a server that works. There are some issues with like YWallet D from mainnet, and sometimes also some issues with the server from YWallet Lite. So I entered the one that Free2Z has gracefully deployed, and so far this one is working pretty well. That's done. Now we just need to rescan, and we scan from the beginning. So this, and then we just have to wait. So this is a recording of a video, so that has been already done. So I already know that that's going to take an hour and 40 minutes. I'm not going to put the entire video on YouTube. That would be pretty boring. So I'm going to cut the parts and edit the parts that are basically the wallet synchronizing. But what we can look at, and I think it's quite interesting, is the memory, the resource usage while this wallet is synchronizing. So for that, I have pulled the resource monitor. Let's see how it looks like. All right, so now we have the resource monitor, and we see that on the CPU side, we have completely picked all the CPUs. This machine is a AMD 5900X, so that's or 3900X, sorry, or 5900X. So it's a Ryzen 2 Ryzen second generation, which has 12 physical cores and 24 hyper-threaded cores. It was top of the line, but that was top of the line like 3 years ago. And so it's a pretty, I think still a pretty fast workstation, but definitely you have better hardware now. You can see that all the CPUs are 100% utilization as we are synchronizing. So the process of importing that many accounts is going to be very heavy on the trial decryption. By the way, these accounts are all empty, so there's not going to be any funds found there. So it's 100% going to be a trial decryption. The trial decryption that's done in YWallet is actually multi-threaded, otherwise the CPUs will not be picked. So we have that. We have multi-threaded decryption, but we also have batch decryption. So we use the API, the batch decryption API from Zcash. By using batch trial decryption, we are saving on some of the ECC elliptical curve arithmetics. Let's put it this way. So, but I think the gain is just a few percent compared to simple sequential ECC. So the batch ECC is not gonna make a huge difference. What's helping quite a lot though is the ability to use all the cores, and that's quite possible because trial decryption is highly parallelizable. Besides that, what you can see is that the network goes pretty steadily, and we had a peak. When the blocks were downloaded, but now it's idle because we are processing blocks, and processing blocks takes longer than downloading them. The way YWallet works is it has a pipeline, and the pipeline has several stages. The first stage is where we download blocks. When we request all the blocks from YWallet in one go. We request, in this case, we would request from block 0 to block 1,700,000 and something. But obviously the YWallet is not going to return. We can see now that there's a new series of block received. So network usage goes up, and momentarily CPU usage goes down. We're going to talk about this phase in a minute. Let me finish about the pipeline description. So the YWallet receives that request for like 1 million blocks, but obviously we're not receiving 1 million blocks and then storing everything in memory. That would be extremely large, and it would overflow the memory. We would have out of memory condition most likely, or at least on small hardware. So what we do is we take advantage of the fact that the API for YWallet is streaming. Therefore, we receive blocks one by one, and we can start processing as soon as we receive a block. So the block that we receive, we can take a peek at what is inside, and we consider the number of outputs that this block contains. So we buffer as many blocks as needed until we get a significant number of outputs. The number of outputs is it's not very important, and I think it should be made variable depending on how much memory you have. But essentially, we cap based on the number of outputs, because this is going to drive how many trial decryptions you're going to need. And when that number is reached, then we emit a series of blocks into the pipeline. We push them into the pipeline. Then while the pipeline processes these blocks, we receive other blocks from YWallet, and we continue buffering them in parallel as the first series of blocks is being processed. So we do that, and then when we get enough blocks also to get a second chunk, we push it, and so on. The trick there is that there's control flow, so therefore the pipeline has can only take one element at a time. So if we push one series of blocks, and then we push and then there's a component that pops it, that takes it, then the pipeline at that level, it will be empty. So we can push another series of blocks. But if the pipeline hasn't finished processing this series of blocks, the upstream component, the downloader, cannot push a second block. It will be because the capacity is only one. So then the channel between these two components is stored, is suspended, which exerts a back pressure into the upstream server, and YWallet will also stop sending us blocks, which allows us to that's why you can see this network ebbs and flow. It's at this moment, because we have as so many accounts and we take so long to process blocks, the network is stalling. We are downloading faster than we can process. Therefore, we go idle. Right? The network downloader will automatically suspend when it happens, and it's suspended at kernel level, so we don't use any resources when this happens. All right, so once the block goes downstream, what happens is that it enters some kind of component that extracts the content of the block, and it looks at all the transactions and the spans and the outputs, and then it distributes that into different workers, so different threads. The number of threads is calculated automatically based on how many CPUs you have, and all these nodes, the output nodes, are distributed fairly evenly, because we know that the amount of time it takes to try to decrypt is pretty much constant. It's just a series of elliptic curve calculation and cha-cha decryption. So it's there's really no loops involved there, and the time is about the same. Once we have the other stuff that is kind of cool is that these thread decryptions are done therefore in parallel and out of order. Everything is uncorrelated. Then once it's done, we collect the results, right? And then we assemble the blocks, because the transactions have to be processed in order. Blocks have to be processed in order. So we have to, when we find nodes that are ours, so 99% of the time, or even more, like 99.999% of the time, the transactions, the outputs will not be ours, and we don't have the plain node, but we still have to process the output node commitment. We have to put that into the tree in order to maintain the Merkle tree of node commitments. So these guys have to be collected, and we put them in the order that they were fan out. So that's done by the next layer. We do that. We build the transactions and the blocks. But this time, when it's something that we own, it's decrypted. Then it continues, right? It continues down. We update the node commitments in the tree. We also use warp sync this is where we use a warp sync to update our witnesses. So these all updates of witnesses is done one series of blocks at a time, and that's how we can manage to be a little fast when it comes to witness updates. Then it continues. It goes to, if we have also transactions, then we have to query YWallet to get the transaction details. So that's done also in parallel by another component. And again, we assemble all the results, and finally we write to the database. So at the end of this process, once the chunk of blocks goes through the entire pipeline, it will no longer be of any use to us. So we just remove the memory. We just drop it. And by dropping that blocks, we also release all the memory that was used. Then once this is done, it releases the lock on the channel, and we are ready to get another series of blocks from the downloader. So you can see that by doing this in a streaming fashion, we have capped the memory usage to essentially like two series of blocks. One series of blocks that is being processed, and one series of blocks that are being assembled by the downloader. So our memory usage here, I can see, I think it's about 300 megabytes. 300 megabytes for 100 accounts. That's actually pretty good. And the best part is that even if the blocks are very empty, such as in the beginning between blocks 400,000 and 1 million, the transactions were the blocks were very empty, only like 1 or 2 transactions per block at most, and very few outputs. But then when we reach 1.720 million, we had this spam attack, and suddenly most of the block had like thousands of outputs. So because the downloader takes a look at the peeks into the blocks, it can make blocks of chunks of blocks of different sizes. And in the beginning, you see that the first chunk is like 500,000 blocks, but then near the end, near the current times, it would be only like 20,000 or maybe even less. So it does slow down significantly, but this slowdown actually is due to a difference in block composition, but it also preserves the memory usage. So if we didn't have that, if we were like just blindly using a fixed value, then we would definitely run out of memory when it comes to like the later blocks. Well, not definitely, but we could run out of memory on the cheaper hardware if we are talking about the later blocks. So the stuff continues, but you can see that the CPU is still pegged at 100. The disk is not very significant because you see these specs, but it's basically the database updates. So they're not very numerous because we only need to write our information, and I think the unit of the disk is not very. So even when it looks like high, it's barely nothing. It's barely anything when it comes to real disk throughput. We are far from saturating on the disk side. The network is yeah, you can see here, for example, that we are finishing a chunks of blocks. So the CPU goes down briefly because we are finalizing the chunks of blocks, and then we are requesting the next one from the downloader. So even though the downloader has buffered a few blocks, as these few blocks get into the pipeline, the downloader has to wake up and start processing more inputs from YWallet D. But we can immediately resume calculation. So the gap is like a few seconds only. So yeah, that's pretty much how YWallet does the synchronization. All right, so now I'm gonna leave it at that. We are now at 1.72 something, which is the range where we are seeing a large number of outputs. So processing will go down. You can see now it shows that the ETA is 20 minutes, 25 minutes. It will probably get worse. It will get slower and slower. But let's let's cut out this part and see how it is at the end. Okay, so now we are near the end. We have of just a few thousand blocks to go, and the pattern is still the same. So memory usage is still the same. So we are still good on that aspect. Let me fast forward a little bit more. Okay, so nearly the end. So actually, this is done. What happened is we synchronize 2 times. We synchronize to if the last height is x, we synchronize first to x minus 3 and then to x, because warp sync only calculates the witnesses at the end. So if we are producing only the synchronization to the latest block height, so to n, then if we were asking to do a transaction or a spend, we usually pick up the nodes that were available at n minus 3, or so then we would not have the witnesses because we only have the witnesses at n. So the trick here is to do a synchronization to n minus 3, so that we compute all the node witnesses at n minus 3, and then we do a short sync up to n. Therefore, we have 2 series of node witnesses at n minus 3, and if the user wants to do a span, then he can use the nodes at n minus 3. So that's the synchronization that's happening now. We synchronize to blah 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 77, where the block height is 80. Right, so now we're doing the final catch up that is going to produce the block height 80. All right, so we are synchronized. Actually, the latest height doesn't change during synchronization. So the synchronization took so long that when we started, we were at the latest block was 80, but by the time we finished, it was 8165. So that's why the last part actually took a bit longer, because we had to also to catch up the part that the blocks that were produced while we were doing the full rescan. So rescanning actually like first caught up to the block height at the beginning of the rescan, and then had to catch up the few blocks that were generated while the rescan was underway. All right, so you have the full process. Again, the whole thing took 1 hour and 40 minutes. And that's for 100 accounts.